wait though. Okay. This is kind of the bonus section, so I think that no stretch of the imagination categorizes what potentially role this section plays on things that are to come in the future. At any rate, so, and that's very intentional because today we're going to be taking our class picture, the final class picture, before we go. So here's the definition. It's very simple. The matrix A is symmetric. If and only if its transpose is just itself. So when we talk about symmetric, this is one of those definitions that's going to have a lot of visual logic to it, because when you look at a symmetric matrix, visually it's going to have symmetry across its diagonal. So here's a little note. This isn't a part of the definition, but it is implied. If I have a symmetric matrix, so if a matrix A is symmetric, then the only way my transpose is going to be the same thing as the original matrix is if there are the same number of rows and columns. Because if I have n by n and then transpose it and flip it around, n by n is not always going to be the same shape. So we need to have A is square. So it's not a part of the definition, but it's just kind of a conclusion that you're forced to make based off of the definition. In some math words, we might even call that a proposition or a corollary or a lemma for all intents and purposes. It depends if you're an analyst or algebraist. So here's our theorem. If A has this special property that we're talking about is symmetric, so basically, if I can take its transpose without changing anything, then any two eigenvectors from different eigenspaces are orthogonal. And G, we didn't just do an entire chapter on this concept. Okay? And so that's going to lead us into this special definition. This kind of the title, or not the title of the section, but the main procedure. An n by n matrix. An n by n matrix. Notice how n by n is a square matrix. A is, and here's your jargon to scare your siblings with. Orthogonally, everyone say orthogonally.
Orthogonally.
And then we combine orthogonally with diagonalizable. That's a tough one to say. Diagonal, and then izable. Okay, orthogonally, diagonalizable. Maybe that'll be the extra credit question. You just come to after the exam and say that 10 times fast correctly. And I'm like, all right, that's half a letter grade in itself. If A has this special factorization, P dP transpose. Now you might be thinking to yourself, P dP inverse is something that we did before with diagonalization, but now instead of the inverse we put a transpose. But because we have a symmetric matrix, those are actually the same. With P, an orthogonal matrix, and then remember when we specifically talked about orthogonal matrices, there was a little property, right? It was that, recall, if I have a matrix where every single column in that matrix is orthogonal to each other, and they've all been scaled to all be unit vectors, then this is the specific type of matrix where its own transpose functions as its inverse. Like if I wanted to invert it, I'm really just doing its transpose. So that was kind of a main application that was really helpful with going to all of the work to put together an orthogonal matrix, was because to get its inverse, all you have to do is transpose it, which is super easy compared to what we had to do in the past. And so that's why this factorization, instead of finding your PDP inverse, all I need to do is find PD and then transpose my PD. And then, of course, what type of matrix is diagonal matrix. So this is basically, I want you to mentally categorize this as the same kind of thing as when we did diagonalization at the end of the previous unit. But then now, just done orthogonally. And the way we do that is through the language of these symmetric matrices, because what we'll find out is that this is only possible, alrighty here, this is only possible if A itself is symmetric. The only case in which this factorization will even exist is going to be if A is symmetric. So, A, an n by n matrix, and bless you, an n by n matrix A is going to be orthogonally diagonalizable if and only if. So that means these two statements are basically interchangeable. They're logically the same exact thing. A, that's crazy, is symmetric. Okay? So that's why we even define symmetry in the first place, is because we find out that that symmetry is the very, very property that is going to allow us to perform orthogonal diagonalization. So here's our example. We want to orthogonally diagonalize the matrix. Is the Matrix any good?
The movie?
Yeah.
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 I'm now realizing I've never seen it.
The original trilogy, first one's fantastic. The first trilogy is pretty good. Don't watch the new one.
3 minus
Yeah.
2.
Don't watch the
Agreed.
new one. I haven't heard good things.
Animated?
The new one is the only one I watched.
Don't watch the animated.
I've never heard of it being animated.
Okay. So here I want all of us to note something. Pretend like there's a little dotted line going through your main diagonal. And then you were to rotate your matrix values around that diagonal. The -2 reflects to a -2. The 4 reflects over to the 4. The 2 reflects to the 2. And of course, the diagonal entry will reflect on itself. So visually, this thing is like literally a symmetric matrix. So if you ever wonder, oh my goodness, is my matrix symmetric? Well, you look at it. And if it's symmetric, then the answer is yes, it is symmetric. Note that A is symmetric. Okay, why am I noting that? Well, because this theorem tells me that the statement that A, oh yes, question.
So is it symmetric when it's a square matrix?
Sorry.
Is it always symmetric when it's a square matrix?
So good question. Not every single square matrix is necessarily going to be symmetric. Like I could create a square matrix and then intentionally smudge out this number and flip it with something else so that it messes up the symmetry. So you can have square matrices that are not symmetric. Being symmetric is like a specific property that is even more specific.
So how do you know that one's symmetric?
This one?
Yeah.
Well, compute what the transpose is. So by definition, I'll know it's symmetric if I take its transpose and it doesn't actually change anything. So if I want to take the transpose of A, what that means is I'm going to take every single column, and instead of writing it as a column, I'll write it as a row. So 3 minus 2, 4. Instead of writing that as a column, I'll write that as a row. 3 minus 2, 4. I look at my second column. Instead of, yeah, you see it?
Yeah.
So that'd be minus 2, 6, 2, 4, 2, 3. And then we think to ourselves, well, you just kind of, that's the same exact matrix. It's the same thing. So this is how we know it's symmetric. Does that make sense? Cool. Now, because I don't want to waste your guys' time, and it won't, and it's not the skill that we're trying to test today, is I'll give the characteristic equation here. So characteristic equation is negative lambda minus 7 squared times lambda plus 2. So it's already been factored for you, so that all we have to do is just identify our eigenvalues. So the usual process for diagonalization is no different. We're going to start exactly the same way. So what are my eigenvalues? Yeah, so we want to find bases for my eigenspaces. For eigenspaces. So I have lambda is equal to 7 to begin with, because I know that if I put 7 in here, it would be 0. And then in here, minus 2. What's the multiplicity here with 7?
2.
So how many vectors should I expect to be to form a basis for this eigenspace? I need 2, yes. Now, you know how to do this from the previous unit. And that's not the specific thing that is unique to the section. So I'm trying to shortcut to where we do the Graham-Schmidt again. So I'll give you what those vectors should be if you do your row reduction correctly. You have V1 is equal to 1, 0, 1, and V2 is equal to minus 1 half 0, minus 1 half 1, 0. So that would be the vectors that form a basis for the eigenspace corresponding to my 7. And then for my lambda is equal to minus 2, how many vectors am I anticipating there being?
1.
Why?
Because the multiplicity is 1.
There's only 1, yeah. And so this third V3, if you go and plug into that process like we did for the regular diagonalization method, you can use it. So if you were practicing this problem, use these as like checkpoints to make sure that you're not making silly mistakes with your row reduction when you're plugging in, when you're doing the A minus lambda I calculation. Okay? So practice doing the A minus lambda I, but that's not the focus of today because that's old material. I've already taught you that. So make sure you have that written down while I erase this and get the next part set up. So what we want to do is we need specifically orthogonal bases for each one of our eigenspaces. That's what makes this is where the procedure will finally deviate from what you already know with regular diagonalization. So I'll articulate that up here so we know what's going on. We want orthogonal bases. Orthogonal bases for each eigenspace. For each eigenspace. Now, that's not too bad because one of these is really easy. It's just a vector by itself. Okay, so we won't have to do anything special with him. However, we have two vectors here that are not orthogonal to each other right now. How do I know that they're not orthogonal? Well, yeah. So, if I took the dot product of v1 dot v2, what I'm doing is I'm taking the dot product of 1, 0, 1 and minus 1 half 1, 0. How would I compute this dot product?
You multiply the first entry of V1 times the first entry of V2, then you add it to the second entry of V1 times the second entry of V2, and then you add that third entry of V1 times the third entry of V2.
Is that equal to 0?
Nope.
No. So this is not equal to 0. What does that mean we can conclude about my vectors v1 and v2? Not orthogonal. Okay. Slight problem. We want an orthogonal basis. What did we learn and spend kind of a gruesome amount of time doing in the previous week? Making them orthogonal to each other, right? So let's actually practice that. So again, since we're already using the letter V, we can just use some other Z instead of V. So we'll set my Z1 vector as my V1 vector. Okay, so that means my Z1 is 1, 0, 1. That I'll use in the formula. Now, if you need to take the time to flip back in your notes to when we did Gram-Schmidt originally, that's totally fine. You're still in study mode. But be able to put the formula together for Z2. How do I compute Z2 from the formula? Let's do the formula first and we'll plug and check. Z2 equals what?
Z2 times Z1
Close. V2.
V2 times V2 minus. Sorry.
V1 dot product V2.
We want V2, right? So we take the vector
Yes.
and dot it with the preceding Z, like the preceding vectors in our orthogonal set, so Z1 in this case. Over what? Yeah.
Z1.
The moment you figure out the correct one here, then it's easy to fill out because it's just copy paste, copy paste, copy paste, and then it goes
Z1.
Z1. Now, you're probably thinking to yourself, why go to all the trouble of relabeling V1 to Z1? Why can't I just put V1 in there? If you understand that and you put V1 in there, you're not wrong because they are the same vector. I'm using this notation to reinforce the fact that if you had to continue to iterate this over and over and over again, you'll confuse yourself more by not being consistent with the way you're giving your formulas with the variables. So if you want to view this as just a projection calculation and put V1 instead of Z1, that's fine. But just be aware that if this was larger than 2 vectors and maybe had 5 vectors to deal with, then this convention is going to be much easier to keep track of in your personal work. Okay? So then we plug and chug. What is V2?
Negative 1 half 1, 0.
Yeah, and I'm just pulling that from the work I would have done previously. Minus, so let's compute these dot products. So V2 dot Z1. And here's my Z1, and there's my, oh, we already kind of did that.
Yeah.
Okay, well that's lovely. It's 1 half. Minus 1 half. Does everybody see where we're getting that from? We already did the work by showing that it was an orthogonal, and that is the same exact dot product. And then the denominator is what?
2.
Yeah. How am I getting that?
Z1 dot Z1.
1 times 1 plus 0, 1 times 1. So 1 times 1 plus 1 times 1 is 2. And then I'm multiplying this by which vector?
Z1.
Yeah, 1, 0, 1. Okay. So if I simplify this, I have minus 1 half 1, 0. That's going to go down there. So plus 1/4, yes?
Mm-hmm.
1, 0, 1, which is really just minus 1 half plus 1/4.
So negative 1/4
So negative a fourth.
plus 5/4.
1 plus
No, just one.
0
0. Oh, yeah.
is 1. 0 plus 1/4 is 1/4. That is my second vector, Z2. Make sense? Okay, and if we want to, for the sake of exercise, because you may or may not need to be able to show that two vectors are orthogonal, let's show that Z1 and Z2 are orthogonal to each other. How would I do that?
Compute the dot product.
Yeah, so Z1 dot Z2 is equal to 101 dot minus 1/4, 1/4. What is that going to be equal to?
0.
Yeah, 1 times that is minus 1/4, a 0, and then positive 1/4. The cancellation is pretty clear. Okay, so do we have an orthogonal basis for my first eigenspace?
Yeah.
Yes, we do. Okay? And now what we want to do, what was the second thing we need to do to our vectors if we want to organize them into an orthogonal matrix? We got them orthogonal, so that's great. There's one more thing we have to do. Remember?
Unit vectors?
Unit vectors. So we'll normalize. That's the math word. We'll normalize all of these vectors. So, do you see why we don't need to do anything special with just a singular standalone vector? Yeah? Okay. So what I'll do is I will... do you guys have these written down in your notes so you can refer back to it?
Yep.
Okay. So, if I want to normalize my Z1 and Z2, so normalize Z1 and Z2, what that means is just make them unit vectors. So with Z1, here's exactly what you would want to do. 1 divided by the length of Z1 times my Z1 vector. Okay, so that is 1 over the square root. And then when I do my formula for length, here's Z1. My Z1 is 101. So it's 1 squared plus 0 squared plus 1 squared here in my length formula. 1 squared plus 0 squared plus 1 squared, all under the square root, times 101, right? Because that's the vector that I'm adjusting. So then I have 1 over the square root of 2. So again, don't worry about changing all of that. You can leave it as 1 over root 2. That's fine. Okay? So 1 over root 2, 0, 1 over root 2. And that is a normalized version of that basis vector. So there's our first U, U1. And then now, let's do the other one. So 1 over the length of Z2 times Z2 is 1 over the square root of what? What am I putting in here?
Wait, that's wrong.
Minus 1/4 squared. Don't forget to square the component of it. Plus 1 squared plus 1/4 squared.
That's fine.
Times minus 1/4, 1/4. So, yes, this is going to be 1/16. That's going to be 2/16 in total. And then you add 16, so you have 18/16. So, another way to think about that. Oh, I should not do that. Do it over here. Bless you. I have 4 over the square root of 18. Because that 16 is a perfect square, and it's going to flip up to the numerator. And then I have minus 1/4, 1/4. So I have negative 1 over the square root of 18, 4 over the square root of 18, and 1 over the square root of 18 if I multiply through. That's are going to be what we call U2. Now there was one last vector that we need to normalize. Now we normalize our V3 that we kind of didn't need to worry about getting the orthogonal basis for from before. Now, before we do that, there's a little cancellation check. Actually, okay, do we have this written down?
Sure.
Maybe. Yeah.
Maybe. Question mark.
Sure.
Let's see what time is it.
42.
Okay. Take the time. We have time.
I'm writing this side of the
Okay.
the right side of the board.
Is the left side of the board locked up for everybody?
My left is your left.
It's the same left.
Yeah, your left hand or your right
It depends on who I ask. If it's the government, I won't answer. Monkeys are dumb.
Okay. We want an orthonormal basis for the eigenspace that corresponds to lambda equals minus 2 now. So we want an orthonormal basis. Orthonormal basis for the eigenspace corresponding to the other one, the other eigenvalue that we didn't do yet. Corresponding to lambda is equal to minus 2. So, you might have noticed, somebody tell me, what was the original V3?
-1, -1/2, 1.
Like that? Okay. We just want an orthogonal vector to start. Well, guess what? It's by himself. So we don't have to worry about orthogonality, meaning that we already have the direction locked up. So scaling it to more convenient values isn't going to mess up this procedure. Because remember, at the end of the day, everything's just going to get normalized and turned into length 1. So the calculations are going to be made easier without the fraction. So we are allowed to select an easier version of this vector, 2 times V3, and normalize this version of the vector because the arithmetic will be way easier to do. Does that make sense? So I know that I'm going to end up scaling this to a unit vector anyways. So why not make my length formula less horrible and choose way easier numbers to then spit it through that length formula so that we can then scale it down. So if you're wondering, oh, I don't know, it seems arbitrary. When am I allowed to scale? When am I not allowed to scale? Does that change the procedure? Here's how you can know. Does scaling this singular vector affect its orthogonality to anything?
No.
No. The only thing that matters is its direction. Furthermore, scaling to get easier values, we're just going to use those same values to go back to the unit vector. So no matter what you do, even if you did it directly from this version of the vector or here, you're going to get to the same exact unit vector. One of them is just going to suck more, and one of them is going to be way easier. So I actually don't care which one you do. I do the easier one because grading fraction mistakes is way harder than grading arithmetic, like integer mistakes. So I can do 1 over the length of my scaled version of V3 times the scaled version of V3. That's going to be 1 over, okay, what's the length of the easier version?
3.
Yeah, because this is minus 2 squared plus minus 1 squared plus 2 squared. And then here's
3.
at minus 2, minus 1, 2. 4 plus 4, so yes, 3. 1 over 3 minus 2 minus 1, 2. So, our last unit vector is minus 2/3, minus 1/3, and 2/3. Is everything happy and well with the world? Okay, cool. And this is then our third unit vector. So, nothing's changed from when we put together orthogonal matrices. My P is going to be the same thing as just arranging my unit orthogonal vectors all together like this. So just U1, U2, U3. So my P is going to be what? What's the first column?
1 over square root of 2, 0. 1 over square root of
Second column?
2. Negative 1 over square root of 18, 4 over square root of 18, 1 over square root.
And the third column? And what's nice about this factorization is, do I need to then compute the inverse of this horrendous matrix? Well, technically, yes. But the inverse is just a transpose. So if I wanted to compute the inverse, P inverse is just the transpose because this is an orthogonal matrix. We've designed it to have all those special properties so that it's going to be orthogonal to each other, and it's going to be unit vectors. So to compute this inverse, just take the transpose of it. So this first column becomes the first row. 1 over the square root of 2, 0, 1 over the square root of 2. The second column becomes the second row. Minus 1 over the square root of 18, 4 over the square root of 18, and 1 over the square root of 18. And lastly, the third column becomes the third row. Minus 2/3, minus 1/3, and 2/3. What's the only thing we're missing from this entire solution? D, right? Our diagonal matrix. That is exactly the same as before. We just want to correspond the eigenvalues to those vectors. So I got my U1 and my U2 from that first eigenspace when lambda was equal to the 7 value. So I want to make sure that those come first, 7 and 7. And then the third column is the one that was with the minus 2 vector. And then make sure we fill it in correctly. You do not have to write P, D, P transpose like that. Like if you find each individual piece, that's all we're looking for, that you can find all those individual pieces. So it's kind of fun to think. You could have started with that original matrix A. This matrix A right here is equal to our P times D times the P transpose. Which definitely is not something that you could do by inspection. But there are some times when I have a policy for myself as a math teacher, like I recognize that I'm actually kind of a numbnut when it comes to doing like brilliant math in your head. So many times I'll teach people who can just do insane calculations mentally that I just can't even fathom doing in my head. But they do it correctly. I've never been one to be a hater. So if you can do better mental math than me, I'm happy with that. This is the only one where I'd be like, that's impossible. No way. No chance. You actually can't do that in your head. Like, there's something, I've been impressed by many things that I could see a realistic path to being like, if you practice really hard and you are really familiar with these things, yes, okay, I could see with discipline and not showering and not eating meals and not sleeping that you could get that good at doing, like, say, integration, but in your head. This, no. So,
How was D determined again?
the 7 and the 7 and the minus 2, those should be very familiar to this problem. What were these bad numbers? Yeah. Same old.
And it's 2 7s because it had a multiplicity of 2.
Exactly. And because it had multiplicity of 2, it spit out 2 columns, U1 and U2. So if I want to make sure that each column kind of is like, You know what this is like? How many of you went to a megachurch service as a kid at least once, right? And so you go and you're like, oh, mommy, don't drop me off. And they go to the sticker machine, because everything's got to be corporate these days, and you punch in a name, and beep, 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 and it says, okay, parent name this, you print out your tags, and your parent's like, all right, turn around, psh, they slap your sticker on the back, send you in, okay? So then when you come, and you're the parent, and you're like, your kids gotta be, they match the parent name that was registered with the kid. That's what the matching is like. So in column 1 spot, 7's gotta go. It's gotta go with mom. Okay? You don't take the wrong kid. Alright? That being said, you would think that people wouldn't take the wrong kid somehow, some way. My little sister, she works with the kids ministry, and the number of times that's just genuinely something that they have to think about and watch for is concerning. And it's not even like they're not even doing it on purpose. People just don't pay attention to which kid just got in. Like, come here, Timmy! And all the Timmys come running, and then you get the wrong Timmy. And then, the church catches, police have to come in. It's not a good time, so match your eigenvalues with their corresponding eigenvector, okay? Make sure that they get to the right guy, all right?
Or the parent.
How do we feel about that problem? It's not terrible, and the reason it's not terrible is because in some sense it's the same exact problem as the diagonalization. All we've done is did a little orthogonal twist in there, and as long as you can keep track of that normalization step, nothing is different. Okay? Any questions for me?
Just to make sure, the whole point is to just get it into PDP transpose form. There's not like another step.
Yes, like the whole function of this is performing the diagonalization. So if you can write it like this, feed that to a computer, now you can start amping up the powers and can do much higher values of computation much easier because the diagonal entry is just going to be scaled up. Okay, anything else?
Could you give us like a 2-minute breakdown of the next exam so we can prepare for this weekend?
2-minute breakdown of the next exam. Okay, well, here's how I'll put it. There is going to be an exam review on Monday, but I'm not going to presume a lot. But let me say this: we covered exactly 6 sections. There are always. I am a really creative feller. One might even suggest I, as a math student, can recognize pattern.
Wow.
And pattern not only in the sense of coincidence, but potentially just common sense. There have been skills that have been demonstrated to you in the lecture recordings. You have forgotten some of those skills, and that's okay, because they were recorded. So you can go back, review those skills, make sure you can do them, spend the weekend, lock in. It's not hard. I recognize that I made them way too much to do with not enough time. So what this does not mean is you kind of slack off now. Just know that you'll actually feel like you can finish this one, okay? So study. Do the skills of the... wait, how many sections were there again in the unit?
Too many.
Oh, there were 6 sections. How many questions are usually on this thing?
6.
What?
Too many.
No. I don't even know. I can't even comprehend what could possibly be. Okay.
And so the bonus is going to be $7.
Alrighty, guys. It's been fun. It's been a pleasure. I have enjoyed thoroughly teaching. Thank you to Dr. Harder for allowing me to basically hijack a second class as an undergrad student.
Is that it?
This is the end of the lecture material in linear matrix algebra. The end of my lecturing at Oral Roberts University Math Department. We will take a class picture. As soon as I turn this recording off, we'll go up to the GC stairs, okay? Does that sound good?
I only use one.
Okay, but pay attention to that.